Welcome everyone to our webinar today. If you're interested in real-time communication and AV1, you are in the right spot. I'm Pierre-Anthony Lemieux. I'm the Executive Director of the Alliance for Open Media, and I'll be your MC today. And joining me is Z Lee from Netflix, who's been one of the main driving force behind this webinar. And this is a good opportunity to point out that the webinar is organized by the Alliance for Open Media. And I'd like to thank our sponsors today, Agora and Meta. And so very quickly, and I promise this won't take long, what is AOMedia? For those of you that might not be familiar with it, it's a collaborative effort to develop royalty-free standards and software for audiovisual media. And it was founded back in 2015. It's an open forum. Everybody's welcome. It has the members from across the video stream ecosystem, content, services, software, and hardware. Very large companies, very small companies, and again, everyone is welcome. So again, this is about AV1 and RTC, and maybe Z, can you tell us a little bit more what we'll be doing today?
For sure. Yeah, we know that AV1 has around for a while, and it's widely used for streaming media. Think movies, TV, and social platforms. But today, we're actually going to be diving into a key question. Is AV1 ready for real-time communications? RTC brings a unique set of challenges. Think about ultra-low latency, real-time network adaptation. You also need efficient coding tool to screen content. We will dive into AV1's technical readiness for those purposes. Another key factor for here to consider is the ecosystem support. We'll examine the status quo of AV1's open source and commercial implementations, both in software and hardware, for different platforms, PC, TV, and mobile. This webinar will consist of two sections. The first section will consist of 3 short presentations, where Eric from Meta, Patrick from Agora, and Alex from NETINT will lead us into AV1 development and deployment in their products, highlights for the benefits of AV1 for their business and their customer needs and the challenges they're facing. After the short presentations, we'll have a Q&A where the audience get to ask questions directly to the speakers. You can do so by typing your questions using the Q&A tool on the right panel of the web platform. Alternatively, you could upvote the questions that you're most interested in. In the second section, we'll bring in 4 speakers, Michael from Google, Sahi from Microsoft, Tahani from Intel, and Patrick from Agora for a panel discussion. And again, the audience, you, will get to jump in to ask questions. So let's jump right in.
Yeah, thank you very much, Z, for that intro. So again, this is your webinar, and your questions are both really welcome, and we'll make this a much, much better event. So please don't hesitate. Don't be shy. Ask questions. If you have a questions, it's likely somebody else has the same question. Upvote questions. And again, we'll start the 3 presentations, and we'll see you again in 30 minutes for a Q&A with the speakers.
Hi, my name is Yu Chen. I'm with the Communication Foundation team in Meta. We work on improving video call quality across Meta family of apps. Today, I'm going to talk about our experience using AV1 to improve the video call quality of real-time communication at scale. AV1 is getting more and more popular in the video industry. Apple and Google has announced AV1 hardware codec support on their new devices. So it seems that adopting AV1 is becoming a trend, and this is favorable for RTC. Last year, we successfully launched AV1 Call on the Messenger app. There are more than 1 billion monthly active users on Messenger. This is large scale and includes devices from powerful desktop machines to mobile phones. I'm going to share what we have learned through our development process. For people who may not be familiar with real-time communication or RTC, let me start with a brief intro. The most popular use case of RTC is video calling. Unlike video on demand, RTC has to deal with end-to-end video latency. Typically, we want to keep the latency to be less than 300 milliseconds. Once the latency goes over, the users start to feel a delay. So it's always a struggle for RTC video system to provide high-quality video while trying to keep the latency low. In this case, we cannot do multipath encoding. The decoder side cannot do much buffering. Any bitrate overshoot will likely introduce video freeze on the code. And the RTC client has to do both real-time encoding and decoding. Both consume a lot of power, so lowering power consumption is critical, especially on mobile devices. So why are we interested in AV1 RTC? Let me show you quality comparison between AV1 and 264. Here, we enable AV1 in the Messenger app and have video calls on two Android phones side by side. Bitrate is restricted to 100 kbps, 264 is on the left, AV1 is on the right. You can see the 264 video is blurry and AV1 is visually better. This is a good example of the benefit of adopting AV1. If we further restrict the network condition to 25 kbps, quality improvement is even more obvious. Low bandwidth networks is an important scenario on Messenger app. This is especially true on mobile devices because we have to deal with poor network condition. The fact that AV1 gives very obvious quality improvement at low bandwidth makes it a desirable codec for us. So we have seen the motivation for adopting AV1 RTC. In the following slide, I'm going to share what we have learned through our development process. I'm going to share more results of AV1 in the first session. I will talk about the challenges we face as well as the solution we came up with. Finally, I will summarize my presentation and share the takeaways. Here's more detailed result of AV1 code on the Messenger app. We just saw a visual comparison at the very beginning. Let's look at the number. These are rate distortion curve, which we usually use to compare coding efficiency of different codecs. The horizontal axis is bitrate, the vertical axis is PSNR. We encode the video at different bitrate. H.264 is the lonely red line. The other line are different AV1 encoding presets. From the top figure, we can see that under the same quality, AV1 saves 30% of bitrate, and under the same bitrate, AV1 improved the PSNR by 2 dB. Because AV1 offers screen content coding tool support, in screen sharing scenario, the improvement that AV1 can provide is even more significant. We can see the evidence of this in the bottom figure. Last but not least, we also observe improvement of user feedback in the A/B test for AV1 on Messenger. And AV1 has several advantages for RTC. First is over better coding tool and so better compression efficiency and better video quality. I've shown you data to support this. And AV1 has RTC coding tool, which enable encoder to quickly adapt to the network during a call. This is critical. In order to handle the change in the network bandwidth, an encoder has to adjust resolution and FPS. However, a change in resolution usually means an encoder has to encode a keyframe. This could introduce a bitrate spike and a video freeze. AV1 provides a tool called reference picture resampling or RPR to solve the problem. The tool allows encoder to encode a keyframe when resolution changes. And finally, there are several scenarios specific to RTC that we have to take care of. Screen sharing is an example. AV1 comes with screen sharing coding tool that can improve user experience. In fact, that AV1 provides this tool at the main profile is a huge plus. So we have shown the benefit of having AV1 on Messenger. Now let's talk about the challenge, how to increase AV1 coverage. The first challenge is that AV1 adds significant computing complexity. This is not surprising. Even though the more advanced coding tool enhance the compression efficiency of AV1, they also require more computing during encoding. The question is that how this computation increase impact the app. We measure the power consumption on the Pixel 8 phone during an AV1 call. we saw 14% power increase compared with 264. It's very challenging to ship AV1 to mobile devices with this power increase. In addition to power consumption, memory usage increase is also an issue. We observe a large memory usage increase on AV1 encoding compared with 264. This results in app crash regression, which I will explain in more detail. Since AV1 code needs more computing resources, the first thing we have to do is to identify the list of devices capable of using AV1. We don't want to cause video freeze or overheating when AV1 is enabled on an ineligible device. We use Meta in-house device benchmarking system to have a reliable list of eligible devices. But our problem didn't stop there. We saw another issue from the A/B test, out of memory crash. We confirmed that there's no memory leak in the AV1 library. The problem is that there might be other background app causing the leak. But with higher memory usage, there is a higher chance running out of memory and triggering the crash. Memory usage increase is correlated to video resolution. So to mitigate the regression, we design a codec switch. AV1 would be initially enabled for low and medium resolution and fall back to 264 for high resolution. In fact, generally, our codec is preferred for high resolution because of power consumption. So before AV1 hardware support becomes available, we think that's a good idea not to use AV1 on high resolution on mobile devices. Besides resolution, we also have to consider some device health measurement, such as encoding latency and even device battery level, to determine if a device has enough computing power or whether it needs to switch to 264. So we found solution for power consumption and memory usage. We got positive results from the A/B test. We also successfully shipped AV1 and made it available on the high-end devices. On Messenger, we have medium coverage on the iOS devices. However, the coverage on the Android device is much less. The problem that blocking us from shipping AV1 onto every device is the high computing complexity. As I mentioned before, compared with 264, using AV1 software encoding will increase the power consumption by 14%. To better understand the encoding complexity, we test the encoding with Open264 and LibLM. We compare several RTC video with different encoder settings. The vertical axis is average BD rate saving. Lower value means better compression efficiency. The horizontal axis is the encoding time compared with Open264 preset 0. Higher value means higher computing complexity. OpenH264 is red line, and each dot represents a different encoding preset from 0 to 2, and the blue line is LibLM. When we increase the encoding preset, a high computing complexity provides a higher coding efficiency, which makes sense. The figure shows that the fastest AV1 encoding preset still take 2.5 times more encoding time compared with 264. This is a problem. We are missing AV1 complexity preset in between, so we can only enable AV1 for high-end devices. If we can have a new ultra-low complexity AV1 software encoder, we will be able to ship AV1 to more devices. In addition, hardware encoder support is also important. For example, Google Pixel 8 has an AV1 hardware encoder support. We tested it, and the results are very encouraging, which can save up to 13% power compared with software 264 solution. So if a cell phone has a good AV1 hardware codec support, it can really differentiate itself among the competitor in an RTC scenario. To sum up, we believe that this is a good moment for the industry right now to adopt AV1 in RTC. A good AV1 software encoder is needed to enable AV1 for more devices. However, AV1 codec support is crucial. If a cell phone has a good AV1 hardware codec support, it can really differentiate itself among the competitor. This marks the end of my presentation. Thank you for your attention.
Hi, I'm Patrick Ferreter, and I lead the global product and marketing teams at Agora. Today, we're going to talk about how we empower developers to build high-quality, real-time communication experiences leveraging AV1. First, Agora is a pioneer in real-time engagement platform as a service, and we provide developers with simple SDKs and APIs that enable them to embed real-time voice, video, interactive live streaming, chat, and AI capabilities into applications. We've been in business for over 10 years and are a publicly traded company on the NASDAQ under the ticker API. Out of our $140 million in annual recurring revenue, we invest heavily with over 35% of revenue back into R&D and innovation to benefit the developer ecosystem. Today, we are proven in scale with over 60 billion minutes a month of video and voice on over 3 billion devices globally. One core piece of Agora's differentiation is our proprietary real-time network, our software-defined real-time network, or SDRTN. This network is engineered for intelligent routing of audio and video traffic over the internet to get around any impairments, and also optimized for ultra-low latency delivery on a global scale in over 200 countries. Agora powers real-time engagement in many vertical applications and use cases, ranging from education, such as one-on-one tutoring, through to live shopping, telehealth, gaming, media and entertainment, and social. Further, our global network is optimized for real-time communications and real-time conversational AI. It's important to support every major developer platform that developers use, as well as support SDK and no-code options for faster time to market for developers, and we've invested heavily to be able to do that. Now, let's focus on developers' needs when it comes to enabling high-quality real-time communication experiences. First, the quality of experience must be consistent and delightful. And this includes under challenging network conditions, such as high packet loss or fluctuating bandwidth. Further, in longer sessions, you really can't heat up the device or consume too much power. So, for example, in longer live streaming sessions or meetings. Next, the experience has to be ubiquitous on the end customer's device of choice, whether that's a high-end mobile or a low-end PC. Next, it needs to work both equally well in native apps as well as industry-leading browsers. It has to be simple to implement. Developers can't be required to know a lot about real-time communications in order to implement the solution. And further, developers have told us that you really can't have complex licensing, and they don't want to deal with complex licensing, including for codecs. Next, it has to support advanced use cases and be very efficient. So more advanced use cases can include multiple streams of video, for example, in live shopping, where you have the seller or the influencer having a video of themselves as well as the product they're trying to sell. And screen sharing is also very common in meeting types of use cases. Next, you need to be able to leverage hardware encoding and decoding where possible and be as bandwidth efficient as possible. So when we look at empowering developers to build high-quality real-time communication experiences, there are three key pillars that we focus on that are required to deliver those exceptional live video experiences. One is optimal image quality. The second is unmatched video fluidity or fluency. And then three is delivery with ultra-low latency on a global basis. So we designed Agora's adaptive video optimization, or AVO, to look at all 5 stages of video processing, which includes pre-processing, encoding, transmission, decoding, and post-processing across device and network, and to provide what is optimal there. AVO uses Agora's coding technology, or ACT, to dynamically adjust the encoder or decoder, or the codec, based on the device capability, as well as interoperability requirements. For example, in some cases, certain devices cannot support certain codecs, or certain browsers cannot support certain codecs. Now, Agora's coding technologies support for AV1 has evolved over time. It's been a longer journey over the last 3 years that began when AV1 was first introduced in Chrome in 2021. We did some testing and we looked at the overall strategy to support AV1, and we decided to embark on our own effort to develop Agora's AV1 to really look at how we simplify the encoder complexity to make it run well on most devices. Again, one of those key tenets that developers require for RTC experiences. I'm happy to say that today, as of Agora's Video SDK version 4.3.1, that we support Agora's coding technology with Agora's AV1. And this has strong rate control algorithms and allows us to have AV1 adapt to support those complex network fluctuations that we talked about earlier, and also is optimized for multiple video streams as well as screen sharing to support the more complex use cases. After the 3 years of work, we're happy to say that our AV1 implementation achieves 12% more compression and has 23% fewer computations versus the typical H.265 implementation in software. Now, let's have a quick demo. And this is of Agora's AV1 versus our H.264, looking at 720p and a software-only implementation. I'm going to play both videos side by side. Okay. And what you should notice is that the quality of these videos and the clarity and the fluency is very similar. But the key call out here is that while H.264 is using 1200 kilobits per second, we're achieving the same quality with only 600 kilobits per second when using AV1. So the key question here to answer is do we believe that AV1, is it ready for its prime time with real-time communications? In the view of Agora, the answer is yes, and it's ramping up right now. If you come back to those key developer requirements for implementing RTC experiences that are exceptional, we look at the current status, and one key area that would be a call out that still needs a bit of work is the mobile device manufacturers and PC OEMs being able to provide support for hardware encoding and decoding at the mid-range and lower-end devices, and then that would help out with these other cases here. However, we do believe AV1 is ready for prime time, and we are scaling it up with our customer base now. And it's exactly how we designed our Agora coding technology to be able to use the best possible encoder or decoder for the situation. So the answer is yes, AV1 is ready for prime time and ramping now. Thank you.
Alex Liu, co-founder and COO of NETINT. Here I'm going to introduce how NETINT VPU enables the real-time AV1 experience. WebRTC is popular in real-time communications. However, it also faces the challenges of network conditions and also limited computing resource on the device side. In the upcoming presentation, I'll explain how NETINT VPU addresses those challenges through innovative VPU features. Here's the topic list. But before we jump into details, I want to give you a very high-level view about our products. In NETINT, we have developed 2 generations of the VPUs. Particularly on the 2nd generation VPU, we called it Quadra. It supports AV1 encoding up to 8K 60 IPS. It also has advanced 2D engine and AI engine, which could be very handy when you want to tackle the challenges of RTC applications. The royalty-free and higher compression efficiency make AV1 the ideal codec for the WebRTC. And with that, the low latency is essential for the RTC user's experience. While using general computing CPU is difficult to meet the high volume demands, our quad VPU is capable of large-scale low-latency encoding by nature. Right? For example, the latency of encode 16 concurrent 1080p AV1 streams, the latency is only about 7 milliseconds. And encoding 32 concurrent 720p AV1, the latency is less than 5 milliseconds. WebRTC is often used on mobile device with low network bandwidth. Quad supports downscaling the input video to lower resolution before encoding, which may improve user experience at a low bitrate. It's also the conclusion from many other companies that they reached the same conclusion. In the picture shown here, the picture on the left is captured from the bitstream with 720p 60 IPS and downscaled to 360p before encoding at 200 bps, which is a considerably low bitrate for the 60 IPS video. On the right side is captured from the bitstream encoded without downscaling, and we can see that downscaling preserves more details as compared to the one that encoding directly without downscaling. And for the performance, the table shows Quadra's multi-lidar transcoding performance test results with a total of 8 lidars, each lidar with 5 runs. The decoder output frames with 1080p resolution and downscaled to 720p, 560p, and other resolution before encoding. In this case, Quad can sustain 30 IPS. In fact, it's much higher than the 30 that is real-time encoding with 8 lidars. Another way to improve user experience at a low bitrate is face recognition and also encoding with ROI, the region of interest. We found it's very useful in these conditions, and Quad supports those. The picture on the left is captured from the face recognition plus the ROI encoded bitstream with 720p 60 IPS at a 200K bitrate. We can see that it looks much better on the picture compared to the right side. You see the face, it preserved many details and makes the quality looks fantastic. And this table shows Quadra face recognition plus ROI encoding performance. Quadra can achieve 22 IPS per session while running 80 drops in parallel. This is running on the open source ULOV4 model. If you have customized the model, I think the performance could be improved further. WebRTC applications also need to dynamically adjust the encoding parameters such as the frame rate and bit rate according to the current network bandwidth. Quad encoder supports frame rate and bit rate reconfiguration, and it can respond to the reconfiguration instantly. As shown on the following example, Quad encoder bitrate is reconfigured per 15 to 25 frames, and the bitrate change is reflected on the output packet size immediately. We also support the dynamic resolution change, which will follow the source. WebRTC users also require the maximum smoothness in the encoder generated bitrate, because the sudden changes in the bitrate may overload the network node and also cause the packet loss. Quad encoder can prevent bitrate spike when the user specifies the restrictive rate control target. As shown in the following example, the Quadra encoder is given a volatile gaming video sequence with static to high motion transitions. The encoder is able to prevent peak rate, which is close to 3900K bps from going over the target bitrate of 2000K. Also, the packet loss is a normal. It is often happened in the WebRTC applications. In the case of the packet loss, most WebRTC applications will need to notify the encoder to insert an IDR frame, also the keyframe, to recover from the video corruption. But which may cause the bitrate spike and network congestion because the IDR frames cause a lot of bits. To prevent this, WebRTC applications can use quadratic encoders reference invalidation feature to recover video corruption without having to insert an IDR frame. In the following example, you can see that the frame 2 is corrupt due to the packet loss, and the diagram on the top shows how frame 3, 4, 5, and so on would be corrupted as well, since they all reference to the corrupted previous frame, unless an IDR frame inserted to break the chain of the reference. The diagram on the bottom shows how reference invalidation works. The receiving node notifies the sending node, which is the encoding node, that frame 2 is corrupted, which makes the encoder change the current frame's reference. Here, we assume the current frame is frame 3 to the nearest LTR, the long-term reference, which is frame 0. So since frame 3 no longer reference to the corrupted frame 2, the video corruption is therefore resolved. The feature is critical to provide the better user experience. So beyond the codec level, Quadro VPU can also provide a lot of value added on the system level. Here is an example of the video conference application. So in that application, SFU architecture is very common. However, when the participants over certain numbers, the SFU architecture is difficult to catch up because they give too much pressure on the network side and also on the client side. So Quadro VPU can help the latency performance by enable the MCU architect. When attached to a MCU server, Quadro can offload the tasks such as the decoding multiple incoming videos, stacking them into one screen, offload background removal, and also background replacement if required, and only output one final video stream and deliver to a user. The following screenshot is the example of using Quadro transcoding with downscaling, background removal, stacking, and customized background replacement. So if you care about the performance, the table shows the Quadro stack filter performance for the video conference application. So Quadro can achieve 30 IPS transcoding with all the features above we mentioned, which can support 49 of 1080p inputs and stack them as a 7x7 screen. Here, I also want to have a quick update about a demo or pattern performed in the IPC. The demo starts from the multiple camera captured on the field, then in a small box, which has SDI cards and also one Quadro VPU. In there, it encoded 4 times of the 1080p AV1 in real time, delivered through the CDN and displayed on the supported device and player remotely. The glass-to-glass latency is only 100 milliseconds, and the quality is very impressive. Okay, that's the wrap of my presentation. Please let me know if you have any questions. Thank you.
All right. Okay. Well, first, thank you very much. A good round of applause, a virtual applause to our speakers. And, well, we have a couple of questions, so I think we'll dive right into it. And I'm going to start with the first one. Let's see if I can work the magic here. Show on stream. Okay, sure now. So the first one is with how featureful AV1 is and how good AV1 RTC has become, are there efforts to add AV1 to various API and standards like WebRTC? Does anybody want to take that? Maybe you, Eric? Oh, you're muted, I think.
Sorry, I was muted. Yeah. Currently, WebRTC does support AV1, and actually, like the contributor is very active this year. Like you can see, if you check upstream, there's a lot of patch recently, like contributing the AV1 improvement to upstream WebRTC, and we Meta also contribute some upstream, some patch to upstream. For example, like we improve the packetization, AV1 packetization method. So yes, like I do see a trend, like people is keeping improving AV1 support in WebRTC right now.
Yeah, I'll further comment that we're working on leveraging our Agora AV1 implementation in our Web SDK, which is fully compatible with WebRTC as well.
Alex, any thoughts?
Yeah, I think the AV1 is getting more popular on the WebRTC and general RTC applications. So we see a lot of the customers start to apply that. So it's really impressive. Yeah.
All right. And since then, following up with a question for you again, Alex, let me just put this up on stream here. What are the bitrate savings you get with incorporating face recognition and ROI, region of interest?
Okay, yeah, that's a very good question. In fact, first of all, it's not only the bitrate saving. In fact, it's making the customer experience is so good and acceptable, right? Compared to previously, they barely can sustain that service. So I think that is the game changer. And if you talk about the bitrate savings, so with extreme low bitrate, the bandwidth situation, we see that there are maybe 30 to 40% of the bitrate savings, which is very impressive. Yeah.
And actually, go ahead.
Yeah. Yeah, I saw there's a second part of the AV1 stack.
Yeah, but before we get to the second part, I'm going to ask my obligatory machine learning question. So do you see machine learning helping ultimately with face recognition and region of interest identification and overall classification? And how do you see that improving encoder performance over the next couple of years?
Okay, I think there are short-term benefits or the improvements and for the long term. I think for the short term, like what we talk about, face recognition or even the dynamic adjust the encoding or the network parameters based on the situation, right? I think that is in the short term, something already achieved, like the face recognition and ROI encoding, and someone are still in the pilot phase, like dynamic adjust all the parameters. We did a very thorough test. It can save about 15% sometimes, but how dynamic to respond to the RTC application, that may take more effort from the system level. That is for the short term. But for the long term, I think we also present some papers that like the latent space encoding or others. I think that will be for the future.
Yeah, I'd say that we've also been focusing pretty heavily on PVC implementations with our customers, as well as region of interest, and looking at how we deploy that, and in most cases make that the recommended default for the best experience overall. So.
Yeah. Oh, is there some network issue?
No, I don't know. We can hear you. Go for it. So, yeah, how would you, do you want to take the second part of the question?
Oh, okay. I'm not sure I'm the best expert to answer that part.
Okay.
I can talk a little bit of our experience because we are working on the LCVC for a long time. I do improve the perceived quality a lot, especially when you achieve the same level of the perceived quality, the bitrate saving from 15 to 35% in that range depends on different contents, right? So that is a very promising new technology. For the VVC, I think maybe Eric and Patrick maybe have better experience, right? We have limited experience with the VVC right now.
Okay, for Meta, like we are always looking for the better codec to improve Meta user experience. But however, upgrading to a new codec is complicated because there are technical and non-technical challenges such as licensing. I'm not the right person to talk about non-technical issues, so let's focus on technical challenges. So I think the main challenge for us on adding new codec to our infrastructure is that could increase our infrastructure complexity, especially if we only enable a new codec to high-end devices. So in this case, we have to maintain different codec in different code conditions. So as a result, we don't want to have too many codec combination in our infrastructure. So the key point is that the benefit of a new codec has to justify the cost of dealing with this added complexity. Here I'm talking about the infrastructure maintenance complexity instead of encoding complexity here. So that's back to the case of AV1. It provides improvement on the compression efficiency, which is good. And more importantly, it comes with RPR and screen sharing content tool support. So in AV1 case, the benefit of AV1 codec can justify the cost. And since we are talking about VVC, like for comparison, like VVC is a good codec option, and it also provide the RPR reference picture sampling. However, the VVC provide the IBC in the main profile, but is missing palette mode in main profile. So in this case, our codec support the VVC, our codec support screen sharing coding tool would be a concern for us.
Okay, thank you. Let's see. Next one I have here in the queue, which actually I think touches a little bit on that. So what innovations are being explored for backward compatibility and smooth integration with existing infrastructure that relies on older codecs, like H.264 and VP8? So, how do we as an ecosystem deploy those new technologies so that we can benefit from them? Patrick, do you want to take a stab at this?
Yeah, sure. I think that we basically, because of our wide range of use cases and developer needs across these use cases and the wide range of devices that we need to support, we designed our network and our end-to-end implementation with our Agora coding technology with this in mind, so that we could adopt new codecs more quickly, look at the device requirements and whether or not they support hardware encoding, decoding. If not, can we support the experience in software, what the network conditions look like, and look at all of this in real time, as well as what developer configurations the developers have based on the experience they need. In some cases, they may need to prefer a higher resolution when network conditions degrade. In other cases, higher frame rate. So we built all of this into our proprietary algorithm and our network to be able to add new codecs efficiently as we can, and as the ecosystem can support them. So for us, this is kind of our core to our business.
Yeah, Eric?
Yeah, and I can add some thought from my side. If we want to deal with backward compatibility, like the typical way is that we like for the old client is just offer the available codec, and then when we start the code, we do negotiation. So in this case, like the new version app, you can check whether the peer side can support a new codec. If not, then the negotiated codec would be 264 or VPA. And also device can also depend on its computing resource to decide whether he want to offer the more advanced codec. And in addition, during a code, as I mentioned, we can even though the two codec is negotiated at the beginning, during a code, we can also have a smart mechanism to decide whether we want to fall back to low battery codec because of we are running out of battery. So there's a lot of trick we can play. But one concern of the backward compatibility is that I don't have time to mention that in my talk during the time limit, but one concern is the binary size. Like, I mean, you can imagine that when we add like more codec into the app, we have like the codec library is keep increasing. So like the binary size is a major concern for the large scale app. So actually that's also referred to my previous what I'm just saying, like adding a new codec, actually there's some concern on like adding complexity. Like I'm talking about like device health complexity or app complexity for maintenance. So that's my 2 cents.
Yeah, I want to say this is more system level effort to provide that. I think both Patrick and Eric provide a lot of good comments about that. So from our side, we are working on the hardware encoder, right, and also be part of the ecosystem. But from my view, we do feel a little bit frustrated, and also I would say that currently, when we build the system, there's still a software first mindset, right? To tackle some of the system level the challenges, in fact, the hardware vendors can be involved more. For example, the issues we talk about, you need to support multiple codecs on device side that will make the code base very complicated and large, right? But how about again, back to the MCU example. How about using the MCU as a bridge, right? You can convert all the different codecs to one that is suitable for the end user, just like traditional streaming, right? Then in that case, a lot of issues can be solved by this bridge or the platform. Instead, then in that case, the application developers and companies can focus on their innovation to the new things. And we use this bridge to help to smooth up the ecosystem upgrade.
Okay, thanks. Now, a question that was asked in the live chat, but I think is a kind of a thread amongst across multiple questions. So what about very low bit rate, very low bandwidth situation, mobile, very low battery, very low power situations? What's the target bit rate? What are the challenges in that particular part of the ecosystem? Maybe you, Eric? So what's low bit rate for you, right, for Meta?
Okay, yeah, like I cannot share the number in our app, but I would say like in the industry, like if the B rate about like 20K and the 30K bps, it's a relatively low B rate for the video. And the
30K, right? 30
yeah,
kilobits per
20K
second.
20K bps. So yeah,
Right.
so and the quality optimization is very different between low B rate and high B rate. For example, like a high B rate, we are looking for like better like frame quality. We want to like have a good encoding algorithm. But the low bitrate, I would say like quality is still important. But in addition to quality, like the reliability is also sometimes even more critical. When I say reliability, let's say for example like video freeze. So like at least like user want to have like smooth video, then we can like looking for better quality. But in RTC to have a smooth video like without freeze is very challenging. As I mentioned, like we have to deal with a lot of like a network case. Like for example, like a 2 case here is very important, like change in network bandwidth and the change and the packet loss. So and AV1 actually like I want to highlight that AV1 it has a very good tool for us. Like it's called like reference picture resampling. I mentioned that in my talk, but I want to highlight that again. Like because like we do find that like in low bandwidth case, actually the network change a lot. So in that case, in traditional codec, let's say 264, if you check your like data, you will see a lot of keyframe due to the change in network, and the encoder had to change in resolution. But AV1, we can solve that fundamentally because AV1 provide like the encoder can change resolution without encoding a keyframe. So this is a huge win for us, like to deal with low bandwidth or poor network condition by using AV1.
We've also seen some cases where even the mobile plan in a region, where basically you're charged by the bandwidth you use and the consumption. So in some cases it makes sense, or the people integrating Agora into their app would want that capability to set that low. And in some cases you can use the capabilities of the device for things like super resolution or super frame rate, but send it a lower bandwidth and complement what the device and the network can do together. So we're also looking at those cases.
So Alex, I think in your slides you had results for 2 megabits per second. Do you also target low bit rate, or is your sweet spot more high bit rate?
In fact, as a hardware encoder, we target for a very wide range of the bit rate and resolutions. For example, the lowest resolution we support is 144 times 128, so it's quite small. And a lot, like you can imagine, a lot of customers using us on the RTC or the UTC contents that really try to get the lowest bandwidth as low as possible. So we get a lot of challenge on that side, and we did a lot of the optimization for that as well. Yeah.
Okay. Maybe next topic. So critical gaps that still need to be addressed to ensure widespread and reliable implementation. So maybe, in your own words, as you're implementing AV1 and deploying AV1, any major gaps left?
For us, I think it was touched on earlier, the ecosystem support for the mobile device providers and PC OEMs for really the hardware support in mid-end and low-end devices. That's going to make our life much easier in wider scale deployment.
So this is a matter of telling the story across the ecosystem, I imagine. Yep,
exactly. We basically have to support the wide range of devices and use cases, and that cuts across mobile and PC, high end to low end. So it's really important for us.
Eric or Alex, any more thoughts on this?
Yeah, I agree with that. Like, for example, like for us, we want to have a good, reliable AV1 ecosystem that's going to help our business a lot. Like I want to share an example. Like for example, like in my talk, I talk about like how we use codec switch to mitigate the regression and make the app more robust. But actually, the codec switch is not free. Like there's some overhead. For example, like every time when you switch codec again, you need to introduce a new keyframe. So I agree. Like if we can have a good hardware codec support and also have like low complexity software encoder support that we can cover the wide range of device situations, then we don't have to switch codec back and forth. That will be super helpful and can improve the user experience a lot. So yeah, that's what I'm thinking.
Okay, thanks. So we're about to run out of time. Maybe we'll go around the panel, the speakers one more time. Maybe one last thought, starting with you, Patrick.
Sure. I think that one of the other thoughts was the intersection of AI and RTC, and a bit more on that. I think we're starting to see quite a few of our customers very interested in generative AI use cases and agent use cases. And we're looking very carefully at the intersection of many-to-many human interaction with AI agents, and also perhaps how codecs have to evolve. Because all these current ones have been designed around human psychoacoustics and human-to-human communication, and it's quite interesting as we look at the evolution here, what could be happening in the codec space to better support that, including tokenization at the device level, right?
What about you, Eric?
Yeah, I want to mention one thing that like we talk a lot on the like traditional RTC case video calling, and actually in addition to video calling, I observed actually there's a lot of new RTC scenario. For example, like avatar calling in which the video is not from the camera, it's from like AI generated avatar, and as well as some like 3D video in AR, VR, and mixed reality use case. So I feel, yeah, there's a lot of opportunity for like RTC, new RTC use case, and the codec and have a good AV1 ecosystem play a critical role to empower those new applications.
What about you, Alex?
Yeah, I think AV1 is an excellent codec, already enabled RTC use case very well. But what we need to do is just to push forward to make it more adoptions from the industry, right? I think that is the whole industry effort, not only the technologies part, but also all the system integrators or even customer side, right? We should push out from all directions. On the other side, I would echo that Patrick and Eric said, right? There are a lot of new things happening in this industry when you combine the AV1 and also the AI, right? So especially like the new generative AI, when in the RTC case, not only the avatar calling or even a lot of the real-time generated voice, right, to communication naturally with people. So that's a lot of new exciting parts that the industry can work together. But from that part, I think, like I said, I think we still a little bit software mindset. So if we want to make this app happen, it has to be the software side, the edge device side, and also from the data center and server side, right? We work all together and bring the hardware, efficient hardware devices into this ecosystem to make it happen sooner.
Okay. Thank you very much, everybody here. We're about run of time, and we should probably give everybody 3 minutes for a short break. And again, if you have follow-up questions in the chat, we have links to LinkedIn for all the speakers, so feel free to contact the speakers directly. Feel free to contact me also through the Alliance for Open Media if you have any questions. And we will see, hopefully, all of you in a second session where we'll get to continue the discussion. And again, thank you very much, Patrick, Eric, and Alex, and a good round of applause. And thank you, everybody, for being for asking those great questions. Thank you again, and we'll see you soon. Bye-bye.
Thank you. Thank you. Bye-bye.